Hi, my name is Trenton Cheng. In this video, I'll be going over our exploration of video file corruption and its effects on model robustness. We'll start by discussing model robustness on videos, motivating our exploration of file corruptions. Next, we overview our setup for model evaluation and simulating file corruption. Finally, we'll discuss our results on the effect of file corruption on model performance. We also qualitatively and quantitatively analyze corrupted videos. Recent machine learning models do very well on video benchmarks like action recognition, but in the real world, video data gets corrupted in various ways, so models deployed on video should be robust to real-world corruptions. Recent work in video model robustness has focused on pixel-level perturbation, but in the real world, videos aren't stored as raw pixels, but in a compressed file format. We're interested in what happens when the bits in the file get changed unintentionally. These are file corruptions. Our goal is to simulate real-world file corruptions and measure their effect on video model robustness. We directly corrupt the bit space of the files and analyze the impact of these corruptions on the performance of action recognition models. Let's discuss the setup for our file corruption experiments. First, we take a pre-trained action recognition model and fine-tune on the UCF101 and HMDB51 action recognition benchmarks. For consistency, all videos are converted to MP4 files with H.264 encoding. We then generate corrupted files and evaluate the model's performance on the resulting videos. Let's explain how we simulate file corruptions. We work with two modes of file corruption: random corruption, where random bits are flipped in the video file, and contiguous corruption, where a segment in the video file is replaced with random bits. In the real world, these errors can happen due to hardware problems, read-write errors, and even cosmic rays. In our experiments, we change the corruption proportion or total proportion of bits in the video file that we corrupt. This is represented here as the total length of orange segments. We now discuss our findings on the effect of file corruption on model robustness. We present results on the HMDB51 action recognition benchmark, but the same trends hold on UCF101, which you can find in our paper. We first noticed that file corruptions cause model accuracy to drop. The x-axes represent corruption proportion. The orange line shows the accuracy of the model at various levels of corruption, and the dotted black line is the baseline accuracy of the model on videos without corruption. On the left, for random corruption, the orange line drops from baseline accuracy as you move right, and we see the same trend under contiguous corruption. This means model accuracy drops from baseline accuracy as corruption proportion increases. To better understand this, we visualize some corrupted clips. Here's some sampled frames from corrupted videos. Note that P is the proportion of video file corrupted. We also mark the accuracy of model predictions with a green bar if correct and a red bar if incorrect. Our main observation is that the model tends to misclassify more visually distorted clips. First, note how as we move down, the visual artifacts get worse as corruption proportion increases. The model prediction changes as well. The top two rows of frames are marked with a green bar, but the bottom row of frames, which shows the highest level of corruption, is marked with a red bar. It seems that clips that look worse tend to be classified incorrectly, so let's see if this pattern holds on clips corrupted in the exact same way. Here's a pair of clips with the same amount of random corruption. Again, we mark the accuracy of model predictions with a green bar if correct and a red bar if incorrect. We observe here that the model misclassifies the more visually distorted clip. On top, in the Apply Eye Makeup clip, which the model got right, the eye and the makeup applicator are distorted but visible, while the walking dog clip is completely unwatchable. As you can see, the more visibly corrupted example is classified incorrectly. For more visualizations, check out our paper. We now measure this effect on the entire dataset. We use pixel space Euclidean distance as a proxy for how distorted a video looks. This metric measures how much each video pixel changed on average. We find that incorrectly classified videos tend to be more distorted. The x-axes show the proportion of the file corrupted. The green line is the average pixel space Euclidean distance for incorrect examples, and the orange line is that same metric for correct examples. We saw that clips that looked more distorted were classified incorrectly, so we might expect the green line to be above the orange line in these graphs if that holds. That's exactly what we see on the left under random corruption and on the right under contiguous corruption. So examples with high average pixel space Euclidean distance are more likely to be classified incorrectly. This means the effect of file corruptions in pixel space may contribute to the accuracy drop we saw earlier as corruption proportion increased. Thanks for listening. In this video, we discussed our experiments with file corruptions. We observed that as the proportion of file corrupted goes up, accuracy goes down. We also noticed that more visually distorted examples tended to be classified incorrectly, and were able to measure this effect using pixel space Euclidean distance as a proxy for how distorted an image looks. Be sure to check out our paper for the full details, and please reach out if you have questions.